Welcome back, ladies and gentlemen. Today we're going to tackle section 11.3, the proportionality of area and volume in similar figures. Up on the screen, you'll see your exit question for the day. I'm going to present to you first with an example. Now, we have done an awful lot of work with similar figures in the past, and this scale factor that relates the two shapes can help us find any amount of missing lengths or perimeters or what have you in that realm. Today we're going to talk about area and what the proportionality is of the area. So things we already know, we can already figure out that the lengths of B to A and the perimeters of B to A are going to follow that scale factor dead on. We know that, we have theorems for that, we've done that work before. But my question to you today is what is the proportionality of the area of B to the area of A? And without further ado, let's just go ahead and calculate it. So if I go ahead and write a ratio of B's area to A's area, I get 36 over 16, which can be simplified to 9 over 4. And maybe you were hoping for that 3/2 to pop up, but it didn't. But it sort of did at the same time. You see, if you take 3/2 times 3/2, you get 9/4. So it's like we took the scale factor and squared it. That was for area. Now, let's take a look at what happens when you do that for volume, and you might want to pause the video and make a prediction here. Now, there's two things that we can there's actually three things we can talk about on a three-dimensional figure. We can talk about length, area, like of a face, and its volume. So, based on our current observations and similar figures, our lengths, one would expect, would kind of adhere to that scale factor. If I took the area of any two faces of small to big, or big to small, however you like, you would expect that scale factor to be squared, and if you do any of the calculations on either one of these shapes, you'll find that to be true. So any ratio of lengths will follow the scale factor directly. Any ratio of area that you choose on either of these two shapes will follow the ratio of 4/25, or 2/5 times 2/5. And what happens when you do it with volume? Well, let's try it. Get the volume of each shape. That's the volume of B right here, 72 cubic centimeters, to the volume of A, 1125 cubic centimeters. Do a little simplification, and you get 8 over 125. And you'll notice that 2 times 2 times 2 is 8, and 5 times 5 times 5 is 125. So it's really like we took the scale factor and cubed it. And that's basically our theorem for the day. Theorem 11.7 basically says that if you have a scale factor relating two similar figures, that the area of one polygon to the area of the other polygon will be simply that scale factor squared. And it didn't mention anything about volume, so I'm going to tack that on as kind of a corollary to this 11.7. It's something you need to be able to work with. But the volumes will have the proportionality of that scale factor cubed. And you'll notice that in all three of these very short little relations that they've gone to each other, the lengths use the scale factor, area uses the scale factor squared, and volume uses the scale factor cubed. And the connective tissue between all three of those statements is the scale factor, so the scale factor becomes very, very important. In other words, you can use the scale factor as kind of a way to connect length, area, and volume between two similar figures. So we can create problems where if I tell you a volume, you might be able to calculate a perimeter given very little information about the two shapes, at least just knowing that they're similar. So it shows you a couple different problems. A very common one right up next: how many square feet are in a square yard and how many cubic feet are in a cubic yard? And you might say to yourself, well, there's 3 feet in a yard, so there should be 3 square feet in a square yard, and there should be 3 cubic feet in a cubic yard. But I challenge you to draw a picture of it, and you'll see that it doesn't work out that way, because the 1 yard, that 3-to-1 ratio, is going to get squared for area, and it's going to get cubed for volume. So if you don't believe me on this, take apart a Rubik's Cube and count up all the little squares that you chopped your Rubik's Cube into. It'd be 27. Except there's a hinge in the middle of the Rubik's Cube. Not that I have cheated on my Rubik's Cube, but maybe I did. Next up, let's do a perimeter and parallelogram. So over in this case, we have a whole bunch of information about B and less information about A, and we are asked to find the perimeter of A given everything we know about parallelogram B. Why don't you pause the video and see if you can go ahead and work with that and get the lengths involved in parallelogram A and just try to figure out if you can do the perimeter. Otherwise, as I've hinted before, the connective tissue between these two is going to be the scale factor. And you notice the only information that we know about both shapes, both figures, is the area. So we might as well go ahead and write a ratio of the area of B to the area of A. If I do that, I get 320 over 20, which simplifies to 16 over 1. And our theorem today said that the ratio of the areas should be the scale factor squared. So that means I have to take a square root of both top and bottom of that ratio that I just got, which is really a 4-to-1 ratio that's been squared. So we know that our original scale factor was 4-to-1, which basically means that any length between corresponding parts is going to be in a 4-to-1 ratio. So including the perimeter, of course. So this length right here, chop it in 1/4 and put it right there. So 8. Take that length right there, divide it by 4 to get 4 right there. And that will be our perimeter. So again, just 4 plus 4 plus 8 plus 8 would be 24 centimeters as a perimeter for parallelogram A. And it's that simple, but you just have to kind of organize the information and figure out, go get that scale factor basically as your connective tissue between all sorts of the problems. Up on the screen, you'll see your assignment for the day and how to do it perfectly. I'll see you next time.